Welcome to lecture 26 on essentials of topology. In this lecture, we will continue the concept of countability axioms. In the previous lecture, we have already studied the concept of first countable spaces and seen a number of examples. In this lecture, we will study a theorem regarding convergence of a sequence in first countable spaces. After that, we will study the concept of second countable spaces and will try to explore the relationship between first countable spaces and second countable spaces. As our motive is to discuss a result regarding convergence of sequence in first countable space, we will begin with the concept of convergence of a sequence. In real analysis, we have already studied this concept. Let X be a non-empty set. Then a sequence in X is a function that is given as from n to x, where fn is given as xn, that is nth term of the sequence, and this is denoted as xn, or this is written as x1, x2, xn, and so on, that is infinite tuple. In real analysis, if we are talking about the convergence of a sequence, so let us take sequence xn in R. We say that this sequence xn converges to x if for all epsilon greater than 0, there exists a natural number, for example n0, such that this xn belongs to this interval, that is x minus epsilon, x plus epsilon, for all en greater than or equal to n0. That is, if this is our x and this is the open interval centered at x, that is x minus epsilon, x plus epsilon, this open interval is containing x, then all the elements when n is greater than or equal to n0 lies in the interval itself. Means only finite elements lie outside this interval. With this definition of convergence of sequence, let us have the concept of convergence of sequence in topological spaces. In a topological space x tau, if we are taking a sequence xn, we say that this sequence is converging to an element x of x if for each open set G containing x, that is, if we are comparing with real analysis, we are replacing the open interval by an open set, there exists a positive integer n0 such that xn belongs to G for all n greater than or equal to n0. What does it mean? Actually, if this is the set x, if this point is x, and if we are taking a sequence in this x tau, if we are taking any open set containing this x, what our motive is, or what we have to show that almost all the elements, that is except finite elements, rest of the elements lie in this open set. When xn is converging to x, we say that x is a limit of the sequence. Also, from the diagram which we have seen here, we can conclude that if the sequence is converging to a point x, it means that if we are taking any open set G containing x, the sequence eventually enters an stage in G. Let us take some of the examples. We are taking xn as minus 1 raised to the power n upon n. This sequence converges to 0 when R is along with Euclidean topology. Let us see the justification behind the convergence of this sequence. That is, G is in tau e and this open set is containing 0, then from the definition of topology, we can construct an open interval that is minus epsilon, which is subset of G, where this epsilon is greater than 0. It can be visualized in this form, that is, if this is our set of real numbers, this is 0. Let us take the open interval like this is minus epsilon and this is plus epsilon. What is going on here, if we are looking at this sequence, that is minus 1 raised to the power n upon n, then we can conclude that we can find some n naught in set of naturals such that the sequence xn belongs to this minus epsilon to epsilon, and therefore this xn also belongs to G. What is the nature of this sequence? This sequence, the terms are positive and negative, so the points will lie in this interval, and this n naught exists because of Archimedean property. Therefore, this sequence converges in R along with Euclidean topology. But if we change the topology on R and we begin with lower limit topology, then this sequence will not converge to 0. Why? Answer is, if we are taking an open set and the open set is, this is 0 to, let us take any point, for example, why not let us take this is 0 to epsilon. So this is an open set in topology, but note that we cannot find any n naught so that the sequence lies in this particular open set, because alternatively the sequence will move outside to this interval. Therefore, this sequence does not converge to 0. Moving to the next example, let us take X as set AB and the topology tau on X is given as empty set X and singleton set. This topology is well known and known as Sierpinski topology. Now if we are taking a sequence in this topology, let us take a sequence xn in X, which is a constant sequence and given by xn equals to a for all n. Now this sequence converges to A. Why? Because if we are taking any open set containing A and there are only two open sets, X as well as singleton set A, these are the open sets containing A, and note that xn belongs to this one and xn also belongs to the singleton set A for all n, and therefore the sequence is converging to A. Interesting fact about this sequence is that this sequence also converges to B, because the open set containing B is only one, that is X itself, and xn belongs to this X for all n. It means that the sequence which we have considered here is converging to two elements. But what we have already studied, whenever we talk about the convergence of a sequence, we always think that the limit of the sequence is always unique. But in topology, what we have seen that the limit of a convergent sequence may not be unique. And this is one of the reason that's why sequences are not much considered in topologies. Now coming to the concept of first countable spaces, and let us try to deduce the result of the sequence in first countable spaces. Let us first have a result regarding first countable space. What this result says, that if we are having a first countable space, then we can construct a countable basis Bx, which is collection of Cn, n belongs to n, and this is countable basis at X, such that Cn plus 1 is a subset of Cn for all n equals to 1, 2 and so on. In order to justify it, because this x tau is already given that this is a first countable space, and if this is a first countable space, then there exists a countable basis at each of its elements. So if we are taking x belongs to x, we can find a countable basis at x. This is a countable basis at x. Now construct a set Cn which is given by intersection of these bi, I is from 1 to n. If this is the definition of Cn, then it is clear that Cn plus 1 is subset of Cn. Now let us take this Bx as collection of the Cn where n belongs to n. So this Bx has a feature, that is Cn plus 1 is always subset of Cn where n is equals to 1, 2 and so on. Note that from this definition, Cn is intersection of or finite intersection of bi's, and every bi belongs to tau, so we can conclude that Cn is also open. Also x belongs to bi, therefore x is also a member of Cn. So actually this Bx is collection of open sets containing x. Further, if we are taking another open set G in tau and G is containing x, then as this is a countable basis at x, we can find out some Bn naught where n naught belongs to n, such that x belongs to Bn naught is subset of G. But from the construction of the Cn, we can also find a Cn naught which is subset of Bn naught, and that is a subset of G, or x belongs to Cn naught which is subset of G. And thus we conclude that this Bx is a basis at x, and note that this is countable because of its construction and the definition of Cn. Moving ahead, let us see this result regarding convergence of a sequence, that if we are having a topological space x tau and A is subset of x, if there is a sequence of points of A converging to x, then x belongs to closure of A. In order to deduce this result, let us recall a result regarding closure of A, that is x belongs to closure of A if and only if for all open sets G containing x, G intersection A is non-empty. We will use this result. So if we are taking a sequence xn where this sequence is from A, and what we are saying that xn is converging to x. As xn is converging to x for all open set G containing x, there exists a natural number n naught such that xn belongs to G for all n greater than or equal to n naught, and from here we conclude that A intersection G is non-empty, or x belongs to closure of A. If we are looking for the converse of this result, note that the converse hold when we assume the space as a first countable space, that is if X tau is a first countable space, then if X belongs to closure of A, there exists a sequence of points of A converging to X. In order to prove this result, begin with first countable space X tau. It is given that this space is first countable, and if this space is first countable for all X belongs to X, there exists a countable basis. Say the basis is this Bx, which is collection of Bn. N belongs to set of natural numbers such that Bn plus 1 is subset of Bn. N is equal to 1, 2 and so on. Now, if we are taking X belongs to closure of A, then we note that for all open sets G containing X, G intersection A is non-empty, and obviously this is a non-empty open set. Note that this Bn, what we have considered, this Bn is also member of topology because this Bx is a basis. Therefore, we can say that this Bn intersection A is also non-empty for all n. Now, let us consider an element of this Bn intersection A. So, what we can get a sequence axiom, and the element of this sequence are from A, that is, this is a sequence in A. Now, if we want to show that this sequence converges to X, let us take any open set G and which is containing this X. Then by the definition of this basis, there exists an element Bn naught in this Bx such that X belongs to Bn naught, and that is a subset of G. And from here, what we can conclude that Xn belongs to G for all n greater than or equal to n naught because of the property available with this basis, as this Bn naught is a superset of Bn for all n greater than or equal to n naught, and therefore the sequence Xn converges to X. That's all about the proof of this theorem. Now moving to the next concept, that is concept of second countable spaces. A topological space having a countable basis is said to satisfy the second countability axiom, or that is known as a second countable space. Precisely, if we are having a topological space X tau, if we can construct a basis for it, and this basis is something like Bn, n belongs to set of natural number because we require a countable basis, then this space turns out to be a second countable space. Let us take some example. The well-known example, that is real line or set of real numbers with Euclidean topology. We also say the Euclidean topology as usual topology or standard topology. This space is second countable because we can construct a countable basis for it, and that is well-known collection of open intervals AB where A and B belongs to Q, that is set of rational numbers. Even if we are taking Rn with Euclidean topology, that's also second countable because it has a countable basis given by Cartesian product of A1, this open interval A1 B1, open interval A2 B2 and open interval A and Bn, where every AI and Bi are from Q, and obviously I varies from 1 to n. Moving ahead, let us take some of the examples which are not second countable. Real line with lower limit topology, we have seen that this space is a first countable space, but interestingly, this is not a second countable space. In order to justify that this real line with lower limit topology is not second countable, assume that this is second countable. And if this topological space is second countable, therefore there exists a countable basis. Let us denote that by B. Now if we are taking any real number, we know that this semi-open interval x plus 1 is a member of lower limit topology, and also x belongs to this semi-open interval. Therefore, by definition of basis, there exists Bx in B such that x belongs to Bx, and that is subset of x plus 1. Now, if we are taking any y in R such that y is not equal to x, so this is clear that this semi-open interval x plus 1 cannot be equal to y plus 1, because it will look like something. If this is x and this is x plus 1, then the second will be something like, if this is y, then this is y plus 1. Also, we can justify that if there exists by such that y belongs to this by, which is subset of this semi-open interval, then bx cannot be equal to by. This is possible because as this bx is a subset of this semi-open interval, if we are computing infimum of this bx, that will always be greater than or equal to infimum of this set x, this x plus 1, which is always equal to x. Also, as x belongs to bx, infimum of bx is always less than or equal to x, and therefore infimum of this bx will always x, and similarly infimum of this by is equal to y. So from here it is clear that bx cannot be equals to by. Now if we are defining a function f from R to B such that fx is equal to bx, then what we have already justified here, that if x is not equals to y, bx cannot be equals to by. This function f is an injective function. But note that what about R? R is uncountable, and this B is countable. So we have constructed an injective function from an uncountable set to a countable set, which is not possible. That's why we reach to a contradiction, and therefore this R with lower limit topology is not second countable. Let us take another example with well-known topology, that is discrete topology. An uncountable set with discrete topology is also not second countable, while we have already seen that this topological space is a first countable space. Why this is not second countable? Again, if we want to justify by contradiction, for example, if we are taking this is x tau and we are assuming that this is second countable, it means that it has a countable basis. Let us take that countable basis B, this B. Also we know that for all x in X, singleton set X belongs to this topology. Therefore, by using the definition of basis, there exists some Bx in this B such that X belongs to this Bx and that is subset of the singleton set X. From here, we can conclude that this Bx itself is nothing but a singleton set X. But note that X is an uncountable set. So what about Bx? This family, that is we are considering this B as Bx where X belongs to X, this becomes uncountable. And therefore, this is a contradiction. Hence, uncountable set with discrete topology is not second countable. Now let us discuss the relationship between first and second countable spaces. We have already seen that first countable space depend on countable basis at each point, while the concept of second countable space is based on countable basis for topology. What we can deduce that every second countable space is a first countable space. In order to justify this result, let us take a second countable space. We are taking that space is x tau. Because this is second countable space, this has a countable basis. Let us denote that countable basis by V. Now, if we are taking any x in X, let us take the collection as B belongs to B, which are containing X, and denote this set as Bx. Now, what property this Bx has? Bx is, this is collection of open sets containing X. Now, if we are taking any open set G containing this X, by the definition of basis, there exists some B in B such that X belongs to B is subset of G. But note that such B we have already taken in Bx. It means that there exists B in Bx with the property that X belongs to B is subset of G. Therefore, this Bx is basis at X, but at the same time this is countable too, because this B is countable. Thus, we have seen that corresponding to each and every element of X, there exists a countable basis at X. Therefore, every second countable space is a first countable space. But note that converse is not true. Why? Answer is, we have already seen that if we are taking an uncountable set with discrete topology, X is uncountable and this topology is discrete. We have already justified that this space is first countable. But We have also seen that this space is not second countable, and therefore converse of this result is not true. Moving ahead, let us see the behavior of subspace of a second countable space, and our result is that a subspace of a second countable space is second countable. In order to justify this theorem, let us take a second countable space x tau. This space is second countable, and because this is second countable, it will have a countable basis. Let us take that countable basis is denoted by this b. Now, if we are taking a subset y of x and we want to justify that this subspace is also second countable, we have to construct a countable basis for this topology. Let us take this by defined as y intersection b. B belongs to this b. Note that because this b is countable, therefore this by is countable too. Also, we have already seen that if this b is basis for topology tau, then this by is basis for relative topology tau y, that is, this is basis for tau y, and therefore this space has a countable basis. Hence, the result, that is a subspace of a second countable space, is second countable. These are the differences. That's all from this lecture. Thank you.